So, welcome back to this new video in mathematics. Today we're going to talk about one of the most important notions in multivariate analysis, and that is total differentiability. So that introduces section 13.3, total differentiability. Now we have already seen that just transferring the one-dimensional concept directly by restricting a multivariate function and working along lines through the variable space is not sufficient to capture the behavior of a multivariate function. So that is why we will try to generalize the concept of differentiability in a different way. The main idea of differentiability in one-dimensional functions was to approximate a function locally by its tangent, or you could say by an affine function. And that is the way that we will use to generalize the idea of differentiability to more than one dimension. So let's quickly make a few notes about this idea, and then we'll see how we can define this more precisely. Okay, so we have already seen that the notions of partial differentiability and also directional derivatives are not sufficient for characterizing optima and local behavior of multivariate functions. So, partial derivatives and also directional derivatives are not sufficient for characterizing local behavior, and in particular local optima, of multivariate functions. So we need to transfer the concept in a more general way. We will transfer the idea of a derivative in a more general way. So the main idea was to approximate a one-dimensional function through its tangent, or through a affine linear function. So in one dimension, the idea was to approximate a function through an affine function locally. And the derivative was an important part of that affine function. It provided the slope. So basically the most important local parameter of that function. The derivative provided the key parameter to that approximation. And that is basically the key idea that we want to transfer to the multivariate setting. So again, the key idea here is to understand a 1D derivative as an important parameter in a affine approximation of a function. Derivative is the most important parameter of a linear, or more general, an affine approximation of a function f at a given point, and let's call that point x star. Then what we have is basically f prime of x star is defined as the limit of x tends to x star of f of x minus f of x star divided by x minus x star. So the approximation that we have is, if x is close to x star, basically we can express f of x as f of x star plus f prime at x star times x minus x star. And you will remember that is the functional description of a tangent to graph f at x star. So basically we could say f of x is equal to that expression plus some error term that becomes smaller as x gets closer to x star. Again, geometrically, what we have here is a tangent. So could also say, we illustrate this in a graphical way. Let's see, let's have a look at some function. Maybe the function will look somewhat like this here. Let's have a function f. So that's the graph of a function f. Choose a point, x star, anywhere, let's say here. So that's our x star. Then this point here is f of x star. And what we do with the approximation is basically we are approximating the function by a tangent through that point here. So that's our approximation. Okay, that is this tangent. And where can we see f prime in this setting? Well, two possibilities. We could either move one to the right here, and if we do that, then f prime, the slope of that line, will be precisely this distance here. That's f prime at x star. Or we could say that tangent can also be characterized by its outer normal, so by a vector that is perpendicular to the tangent, and then that vector is minus f prime at x star and 1. Okay, so that's the normal vector for the tangent. Okay, so if you wanted to write that tangent in a vector form, then we could also write it in this way, minus f prime of x star and 1. So this is this normal vector transposed times x, y is equal to minus f prime of x star and 1 transposed, and then a point that is on the graph, and that of course is x star and f of x star, right? And you can see if you just multiply that, then you get back to the functional description above. Yeah, so the functional description of the tangent that directly follows from this is y equals f of x star plus f prime of x star times x minus x star. And this expression is now something that can be transferred to higher dimensions. So that is what we will do. We're going to transfer this idea here to higher dimensions. To give you a rough idea of how this could look, let's again have a quick look at a graph, this time in 3D. So basically, this is x1, x2, x3 here, or f of x1, x2. Then we need a graph. So let's again take a very simple example. We just use a parabola here, some graph that looks like this. Okay. And we want to approximate that through a linear function locally. So what does that look like geometrically? What we do here is we choose a point somewhere in that plane here that corresponds to a point on the surface of that graph. So that is x star, that other point here, that is f of x star. And then we want the local approximation, and that approximation now is again a tangent, and of course we don't just get a line. This is a higher dimensional approximation. So in this case we approximate the thing by a plane, yeah, that is tangential to this point here. So yeah, it's probably hard to see, but we'll have a plane that somehow looks like this, that goes through this point here. So that's a tangential plane at the point x star f of x star. Okay, we fit that one. And you will see that these tangential planes, those can also be described using the outer normal vectors. So you can also describe those through a vector that is perpendicular to the plane. And this vector here, this will have the exact same form. That's going to be minus f prime of x and 1. Okay, now that's the idea that we want to transfer, and let's do that. Let's see how we can get this into a precise definition. So the main point of today's video, this definition here. Again, we'll start with a set x, so let x be a subset of R to the n. We'll use an open set for convenience. Let f be a function defined on that set, and let x star be a point in that set. And if you don't use an open set, then of course you have to use an interior point and restrict everything to a suitable neighborhood of that point. Okay, then f is called totally differentiable or just differentiable at x star if there exists a vector, we call that G, in R to the n, and this vector will provide the linear approximation. So we need a vector, and we also need a function R that will be the remainder of the approximation. So whatever error the approximation has will be captured by this function, and this function will be defined on a neighborhood around the origin, and we'll map to R. We'll measure an error for some delta neighborhood of the origin, such that the following holds. F of x can be expressed as f of x star plus G transposed x minus x star. And you can see this G is now taken the role of the one-dimensional derivative, plus this approximation is usually not exact, of course, so we'll have an error, and this is exactly this R, and the error should depend on the difference of x and x star. So if x is equal to x star, then the error should be 0, and it should become smaller as x approaches x star. And of course we'll have to impose a condition on that error. So the question is, how fast will that become smaller? And that's what's expressed in this condition here. So limit as x tends to x star of R of x minus x star divided by the norm of x minus x star. So the distance of these 2 points is 0. So the idea is that this remainder, this arrow, goes to 0 quicker than the distance of x and x star decreases. Okay, so let's make a note of these points. So what the G does is provides this linear approximation. So G provides a linear approximation to f locally at x star. Yeah, so this whole thing is locally around x star, and locally this approximation is good in the sense that the approximation error tends to 0 faster than the distance between a certain point in the neighborhood and the point x star itself. Okay, so the second point is locally, meaning around x star. The approximation is good, meaning the error R tends to 0 faster than the distance of x and x star as x tends to x star. Yeah, so in other words, the error is small compared to the distance. At least locally in some neighborhood of x star. Finally, let's fix notation. This vector g, or g transposed, that's also known as the differential of f at x star, is called differential of f at x star, and is often written as capital D, f of x. It's also sometimes just written as f prime of x at x star. Yeah, so this is called the differential. And this D, by the way, this is also referred to as a differential operator. Okay, and finally, second part of the definition, of course, a function is differentiable on its domain if it is differentiable for every point. A function is called totally or just differentiable if it is differentiable for every point in its domain. Okay, so this is the definition of multivariate differentiation. We'll see a few examples in one of the next videos. Before that, we'll specifically have to deal with one question. And that is the question if this is really valid in the sense that it extends our one-dimensional definition. It hopefully does. But of course, the definition we just wrote down could also be applied to one-dimensional functions. So the question is, what happens if we do that? What is the connection to our usual definition of one-dimensional differentiation? And of course, there should be a connection. And we claim that this is actually an extension. So this definition is an extension of 1D case, meaning it includes that one-dimensional case as a special case. And we'll have a look at that. So consider a function f from R to R that is differentiable at some point x star in R in the usual one-dimensional sense. And the question is, if this function is also totally differentiable, is that differential that we get, is that actually the derivative, the one-dimensional derivative? And it will turn out it is. So if f is totally differentiable, then that means there is a g, in this case in R, and there's a function r that's defined on some neighborhood of 0, so in some interval minus delta to delta 2r, such that, well, f of x is f of x prime plus g x minus x star plus r x minus x star. Okay, and that r hopefully tends to 0 quicker than x tends to x star. And that's what we're going to investigate now. So if that is the case, then r of x minus x star needs to be equal to f of x minus f of x star minus g x minus x star. So we know that the limit of rx minus x star over the absolute value of x minus x star, we know that this limit here, as x tends to x star, this is 0 if the function is totally differentiable. Okay, so what we get here is, this is the same limit as, well, just calculate what r is. So this is the limit of f of x minus f of x star minus g of x minus x star over the absolute value of x minus x star. Okay, and now we'll have to deal with that absolute value, and to do that we're going to make a case distinction. So that means, in particular, case 1, let's first consider the limit as x approaches x star from above. So x is greater than x star. Of course, this limit is then also 0. And let's copy that first. Oh, sorry, f of x here minus f of x star minus g x minus x star. And then this absolute value can just be forgotten about, because that expression is always non-negative. Okay, so what we get in this case is g equals the limit of x goes down to x star, f of x minus f of x star over x minus x star. Right, and that is precisely the definition of a one-sided derivative in one dimension. So let's see if the second case works out as well. In the second case, we'll have a look at the limit as x approaches x star from below. So in that case, the absolute value then becomes minus x minus x star. So again, if we solve that for g, g is again the limit x up to x star of f of x minus f of x star over x minus x star. So the limit agrees, and that means g is exactly that limit here. And that, by definition, is the derivative, the one-dimensional derivative of f at x star. Yeah, so what we get here actually is, for that specific setting in one dimension, d f of x star, the total differential, is precisely the same thing as f prime of x star in the usual one-dimensional sense. Okay, so the one-dimensional case is contained as a special case in this definition of a total differential. Okay, now of course there's a couple of questions we still have to answer. One important question is, how do we actually compute this total differential? Are there any nice differentiation rules like we know from 1D? And what is the relation of this total differential, if there is any, to partial differentiation and to directional derivatives? And one question we didn't even ask until now is that differential even uniquely determined? Or may there be more than one vector that does it? So these are questions that we'll have to answer in the upcoming videos. But before we'll do that, we'll first have a look at some examples of total differentials to see how these may look.